So today we will again discuss a problem from IIT Advanced 2026 question paper. This time it is the turn of physics, and as we did in the last case, this will be a question with multiple correct options. So you have to evaluate each and every option. Let me just read out the problem. In a vacuum chamber, a particle charge is equal to 1 microcoulomb and mass is equal to 1 milligram is projected with a velocity I cap plus 2j cap meter per second from the xz plane at time t equal to 0 in an electric field of 1 I cap volt per meter. At t equal to 0.2 second, the electric field is switched off and a magnetic field of 6 j cap Tesla is switched on. Then the correct options is or are G vector is equal to minus 10 cap j meter per second square, a data which is practically known to each and everyone. G vector acts in the vertically downward direction, so it is along negative j cap. Option A, the vertical distance of the particle from the xz plane at t equal to 0.3 second is 15 centimeter. The vertical distance, option B, the vertical distance of the particle from xz plane at t equal to 0.4 second is 10 centimeter. Option C, radius of the trajectory for the particle at t greater than 0.2 second is 20 centimeter. Option D, the particle will be in the xz plane at t equal to 0.35 second. This is the problem statement. Let us now go ahead with its solution. As I said, it's a question with multiple correct options, so we have to judge, we have to analyze each and every option. We will start with the time period, with the time interval lying in the closed interval 0 second to 0.2 second. 0.2 second, as you have all seen, is quite a pertinent data for this problem. For this time interval, the particle is under the influence of the electric field, which is 1 I cap, and also the acceleration due to gravity. So resultant acceleration of the particle is this will serve as equation number 1. This is quite simple. This should be known to everybody. The electric force is Q into E vector. So divided by the mass of the particle, it gives us the acceleration, and G vector was always there. So its charge was 1 microcoulomb and its mass was 1 milligram, a data value which many students can make a mistake about. So you have to convert that into kg. So A vector turns out to be equal to that is in the time interval 0 second to 0.2 second, both the upper and lower bound inclusive, the acceleration vector of the particle is given by equation number 2. The initial velocity of the charged particle is given to be this is our equation number 3, and the vertical position of the particle is y naught equal to 0. It is not directly given. How do we know about it then? Because it is clearly mentioned in the problem. Please read the problem statement very carefully. It is clearly given in the problem that the particle is projected from the xz plane. So its y coordinate at t equal to 0 should be 0. That is why we have written that y naught equal to 0. So velocity of the particle at t equal to 0.2 second, it should be obtained by the simple one-dimensional kinematical equation. Because why? Let me just tell you. Newtonian kinematical equation, because the particle is having constant acceleration. The acceleration is independent of the space or time. So we will employ these equation, and despite that there will be hue and cry that IIT papers, IIT problems are very tough. It is not tough, it is conceptual. See, in place of t, we have put 0.2 second because t, we are calculating the velocity of the particle at t equal to 0.2 second. So, if we simplify this, we should be able to get very easily, without any doubt, that v vector is equal to 1.2 j cap. The x components cancel each other out. So, the final velocity of the particle is along y direction. Then, vertical position of the particle at t equal to 0.2 second is again Newtonian kinematical equations, because the acceleration involved is constant. Y equal to ut minus half at square. So the initial speed was given to be equal to the y component is 2. See this, the y component of the initial speed was 2 meter per second. Time is 0.2 minus half into 10 into 0.2 square, which turns out to be equal to 20 centimeter. This is equation number 5. So y is equal to 20 centimeter. This is equation number 5. So now we have to change the page. Now, as time keeps on elapsing, for t greater than 0.2 second, the electric field is switched off and a constant magnetic field 6 j cap Tesla is turned on. So when a magnetic field is turned on, the charged particle will be experiencing Lorentz force. This is too simple. The Lorentz force is this is the Lorentz force that the particle experiences. So these upon calculation turns out to be equal to 7.2 micronewton, that is 7.2 into 10 to the power minus 6 Newton in magnitude, and it will be in the direction I cross j. So FL vector, you must be knowing what I cross j is equal to. I cross j is k cap. I cap cross j cap is equal to k cap. It is 7.2 micronewton. So the Lorentz force on the charged particle acts in the z direction. That is why we have got this k cap. Then the vertical motion controlled by the gravity remains uninfluenced. Listen to this point once again. Since the Lorentz force acts in the z direction, that is along k cap, then the vertical motion controlled by the gravity remains uninfluenced by the Lorentz force. The Lorentz force has got nothing to do with the gravitational force. It doesn't influence it because the two are in the separate direction. The two are mutually perpendicular to each other. So at any general time interval t dashed, which presumably has to be greater than 0.2 second because the magnetic field is turned on after 0.2 second. The vertical displacement of the particle is given by Let me just explain the meaning of all the terms in this equation, which should be familiar. It shouldn't create a problem in my view, but still just mentioning once again. This is the initial speed as a function of t dash because we are considering a time interval t dash which has to be greater than 0.2 second. and the displacement which the particle already had when the electric field was switched on, must be taken into consideration. That is why, which we have already found out. That is why we have written down equation 7 in this format. So now, equation number 4, if you need to go back, then just see the previous portion of the video. From equation number 4, the initial velocity of the charged particle along y direction was 0. Because the speed was calculated to be equal to 1.2 I cap. Go back to equation number 4. The velocity vector was calculated to be equal to v vector equal to 1.2 I cap. So its z component, its y component is 0. That is why the initial velocity of the charged particle along y direction is 0. And y, we have calculated y from equation number 5. It is equal to 20 centimeter. You shouldn't have forgotten that. So when t is equal to 0.3 second, that is what we need to write for what is t dashed? The interval is just 0.1 second long, because t dashed is 0.3 second minus 0.2 second. So t dashed is equal to 0.1 second. So this t dashed which we are going to put over here is equal to 0.1 second. So plugging those values in, plugging those data into equation number 7, we straight away get where 20 centimeter has been converted into meter. Please keep that into mind. If you do this calculation, you are straight away going to get yt dashed equal to 0.15 meter, which is 15 centimeter. This is our equation number 8. And from equation number 8, very clearly, read out option number A from the question. From equation number 8, very clearly, option A is correct. So I reiterate, option A is correct. Now, this is the time to cross-check option number B. For that, t dashed being equal to 0.4 second minus 0.2 second equal to 0.2 seconds. So the time interval for judging option B is 0.2 second long. Y is as usually 0.2 meter, because it came to be equal to 20 centimeter. When we convert 20 centimeter into meter, this is what we get. And ut dashed is 0. Now, upon putting those data value in equation number 7, this turns out to be equal to 0 meter. Let us tag it as equation number 9 for our purpose. And from these equation number 9, very clearly option B is incorrect. So B is incorrect or invalid. Now the Lorentz force is along k cap, and as seen from equation number 4, the velocity vector of the particle was along I cap. So the trajectory should be a circular trajectory. Very common formula for the radius of the circular trajectory followed by a charged particle when fired into a magnetic field of uniform magnitude is R equal to mv by qb. Now if we put the value of m, if we put the value of v, q and b, we get this is equal to 0.2 meter, which is equal to 20 centimeter. And this radius will be serving as equation number 10 of this problem, which we have almost finished. So very clearly, from equation number 10, option C is correct. So equation number 10 renders option C as correct. So A and C are correct, B is incorrect. Only D remains to be analyzed, but that is very easy. The vertical distance of the particle from the xz plane at t equal to 0.3 second, which is option A, and at t equal to 0.4 second in option B, have already been calculated. So it is not possible for the particle, let me just write it down. So it is not possible for the particle to retrace its path at t equal to 0.35 second, which is intermediate to 0.3 second and 0.4 second, which lies in between 0.3 second and 0.4 second in the xz plane. No mathematical calculation, this simple conceptual thought renders option D as incorrect. So option B and option D are incorrect for this problem, while option A and option C are correct. What did we need to solve this apparently tough looking problem? Basic idea, very basic idea of electromagnetism. Radius of a charged particle moving in a circular trajectory inside a uniform magnetic field fired perpendicularly into it, and basic one-dimensional kinematical equation. I hope that I have been able to illustrate that this problem might have been a little long as a problem, but it was never a tough problem. If your conceptual ideas are correct, then you can very easily solve this problem to get full marks.